Welcome all. In this particular lecture, we will discuss about equivalence relation and classes. So, what is an equivalence relation? An equivalence relation on a set is a relationship x is equivalent to y between two elements x and y belonging to S, in which the definition of the symbol equivalent must satisfy the requirements of reflexivity, that is x is reflected to x, symmetry. If x equivalent to y, then it implies that y is equivalent to x, transitivity, and that is x equivalent to y and y equivalent to z imply x equivalent to z. So, this is the definition of the equivalence relation, and these are the requirements for the equivalence relation. Now, it may be shown that an equivalence relation on a set S divides up S into classes Ci such that x and y belong to the same class if and only if x equivalent to y. I am again repeating, that is x and y are two elements and they belong to the same class if and only if x equivalent to y, and every element w of S belongs to exactly one class. So, it can be shown. So, how to show that? Let x is an element that belong to S, that is the original set. X is an element of that particular set. Now, let us define a subset Sx, that is Sx is a subset corresponding to the set S. Now, in this subset, and this is a subset of all elements u of S such that x is equivalent to u. So, at first what we have defined, that is S is a set, and in that particular set x is an element. Next, we are defining a subset Sx, a subset Sx of S, and it is a set of all elements u of S such that x is equivalent to u. So, in the subset u is a general element. Actually, the u elements are contained in the original set S, but we have constructed a particular subset Sx containing such elements u, and it is such that x is equivalent to u. Now, clearly by reflexivity, x belongs to Sx. Why? Because as x is equivalent to u, that is why we are saying that is x belongs to the subset Sx. Now, we assume that x is equivalent to y. Suppose first that x is equivalent to y. We are assuming that x is equivalent to y, and we also assume that z is an element for the subset Sy. Z is an element for the subset Sy. Then y must be equivalent to z, because in Sy subset there is y, and z is an element for the set subset Sy. So, y should be equivalent to z. Now, as x is equivalent to y and y is equivalent to z, so using the transitivity, x must be equivalent to z, which means that z belongs to Sx, because if x is equivalent to z and x is contained in the subset Sx, so z also belong to the subset Sx. Conversely, since the symmetry law gives y is equivalent to x, if x is equivalent to y, then y is equivalent to x. Now, if z belongs to Sx, that we have just shown before, if z belongs to Sx, then this implies that z also belongs to Sy. If z belongs to Sx, then this implies that z also belongs to Sy. These two results together mean that the two subsets Sx and Sy have the same members and hence are equal. So far what we have shown that Sx and Sy have the same members and hence are equal. Now suppose that Sx equals Sy. Sx equals Sy. Since y belongs to Sy, it also belongs to Sx. Because Sx equals to Sy, and since y belongs to Sy, it also belongs to Sx, and hence x is equivalent to y. So what we have shown here, that is we have started from assuming that x is equivalent to y, and lastly we have shown that Sx and Sy have the same members and hence these subsets are equal. Next what we have shown that suppose Sx equals to Sy. We have started from here, and next we have shown that since y belongs to Sy, it also belongs to Sx because they are equal, and hence x is equivalent to y. So this ultimately completes the proof of the statement 1. The statement 1 is that x and y belong to the same class if and only if x is equivalent to y. But the next statement is immediate corollary of the first statement, that is every element W of S belongs to exactly one class. The most important property of an equivalence relation is as follows. Two different subsets Sx and Sy can have no element in common. For example, before we have shown that if Sx equals to Sy, then they have some common element. So conversely we can say that is two different subsets Sx and Sy can have no element in common, and the collection of all the classes Ci is a partition of S. That is, we can partition S in different classes, and that is every element in S belong to one and only one of the classes. So we can also prove this. Suppose Sx and Sy have an element Z in common, then x will be equivalent to Z and y will also be equivalent to Z because Z is common for both the subsets. And so by the symmetry and transitivity laws, x is equivalent to y. So if x is equivalent to y, by the above theorem, this implies that Sx equals Sy. But this contradicts our assumption, that is Sx and Sy are different subsets. So Sx and Sy can have no element in common. In this way we can prove this. Finally, if the elements of S are used in turn to define subsets and hence classes in S, every element U is in the subset Su. Suppose we are partitioning S and we are constructing different subsets. So every element U will be in some of the subsets Su, that is either a class already found or going to constitute a new one. But whatever be the case, every element should be contained in a particular subset, and it follows that the classes ultimately exhaust S. That is consisting all the classes, ultimately S can be formed. That is, every element is in some class. So that is the concept about the equivalence relation and the class. I hope you have understood this lecture, and for further understanding I refer you to go through the textbook of mathematical methods for physics and engineering by Riley, Hobson and Benz. And thank you for listening the lecture.